Hello, this is Lab 3 on magnetic fields. To begin, the purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet, which we will use a magnetometer to measure. And using this data, we will calculate the magnetic moment. We will also create a visual representation of the magnetic field of a bar magnet on GlowScript and indicate the magnetic field at an observation location 45 degrees off axis at a distance d. To set up the experiment, I first zeroed the x component by adjusting the direction of the phone, then marking the horizontal component with a ruler. Next, I had to find the location of the magnetometer on the phone, and I did this by sliding the phone horizontally and vertically along the ruler while the magnet was on the end and marking with tape the location at which the magnetometer shows the greatest value. Once the experiment was set up, I was able to record the different readings as we moved the bar magnet along the yardstick until we reached the desired components. To get the measurements for the off-axis magnetic field, we would slide the phone along the rulers. These tables depict the data collected along the averages of the trials. Some of the observations made from the experiment include that when the magnetometer was closer to the magnet, we noticed the x component of the magnetic field increase. On the other hand, when the magnetometer is far away from the magnet, it measured a net zero value in the x direction. Then, using the data and the following relationship on the magnetic field, we were able to find the magnitude of the magnetic moment of the bar magnet was around 2.8832. Next, we will go over the GlowScript code that helps depict the magnetic field of the bar magnet. We will want to create a function in the code using the general equation for the magnetic field of a dipole in order to accurately depict the magnitude and direction of the magnetic field. In addition, we will find the magnetic field off-axis at a 45-degree angle and at a distance d away. Going through the code, the steps goes as follows. First, we want to create a method to calculate the magnetic field. Then, we create arrows to represent the magnetic fields using the calculations in step 1 to determine the direction and magnitude. There are 2 arrows used to show the on-axis magnetic field, which are in orange, and 4 arrows to show the perpendicular components that are in cyan. Lastly, we will use the average perpendicular distance we got from our experiment as d in order to solve for the magnetic field 45 degrees from the axis at that distance d away. In the final results, you can see that the perpendicular components are similar and have a vector of negative 2.883 e to the negative 700. And for our observation location at a distance d that is also 45 degrees, the calculations show that ends up with a vector of 1.4414 e to the negative 7, 4.3245 e to the negative 7, 0. So, some last minute questions we would want to consider. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? In this scenario, we would see that the components would be much larger or smaller depending on the orientation, and that we would have to consider these initial values without the effects of the bar magnet when doing our calculations. Next question. What if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect the measurements to differ? Well, overall we would see an increase in the magnetic moment, an increase in the magnetic field, but we would see that it would be in the same direction because we would have about twice the magnet, but it would be oriented the same, and overall when they were connected, they just create one larger magnet. And that's why we would have these results with the same direction but just a larger magnitude. And that concludes Lab 3 on magnetic fields.